Cool. Hello, everyone. Welcome to another Wednesday evening at Cambridge University Astronomy. This week, we have a bit more of a cloudy evening, unfortunately. The last couple of weeks, we got some stargazing in. This week is the first week we're completely clouded out. But luckily, we have two very excellent talks for you. So we're going to have our headline speaker, and then we're going to hand over to the CAA, who are going to talk about the closest very big black hole. But before that, I'm very happy to introduce our headline speaker. We have Dr. Naomi Robertson, who is a postdoc in the Kavli Institute for Cosmology, and she's going to tell us all about the dark universe. Yes, with that, over to you, Naomi.
Thanks, Matt. So I'll just get started. There we go. Great. Okay, so over the last century, our understanding of the universe has progressed very rapidly, and it's actually a really exciting time to be working in the area of cosmology. So within cosmology, we are trying to figure out the recipe for how our universe was made. From when Einstein's theory of general relativity was first published, there has been huge developments in the theoretical description of our universe at the largest scales. And now we are collating the data sets required to rigorously test these theories. Amazingly, so far, all these independent observations seem to support one theory. However, I have to confess that even within this really well-supported theory, we can't explain 95% of our universe. So this means that the stuff that we can see and know what it is, i.e. everything from you and me, the screen you're currently staring at, the chair you're sitting on in your house, the Earth and the other planets in our solar system, and the sun and the stars in our galaxy and other galaxies, all of this only accounts for 5% of the universe. Now we know the other 95% exists because we can see its effect on regular matter, but we don't know what it is yet. So some of our most accurate measurements of what makes up our universe were made by the Planck satellite, which is shown here. So this was a European Space Agency mission to look at the universe when it was just 380,000 years old. So this may seem still pretty old, but comparing this to how old the universe is now, which is nearly 14 billion years old, this is essentially like taking its baby photo. So from this data set, we found that the universe is about 5% baryons, which is the stuff we know and we can explain with particle physics. Then we think there's this stuff called dark matter, which makes up about 27% of the universe. And finally, dark energy, which is just less than 69%. So the term dark comes from the fact that we can't see these entities directly. Now, this may seem like a bit of a disaster. You know, there's 95% of the universe that we can't explain, but it's also really exciting because to be able to explain the dark universe will require some incredible discoveries. So how did we figure out that these dark parts of our universe exist, and how do we go on figuring out what they actually are? So looking out into the universe, we see stunning galaxies like this one. Now, many of you have probably seen this one before. You may have been lucky enough to see it with your own eyes through a small telescope, as this is our nearest neighbor, the Andromeda Galaxy. So these galaxies contain hundreds of billions of stars, which all sit in this disk-like structure that you can see here and rotate around the middle. So it's the force of gravity that holds these stars in place and stops them from flying off into the vastness of the universe. So if I imagine having a weight tied to a bit of string and then spinning this weight around, the faster I spin the weight, the tighter I have to hold on. Equivalently for our galaxy, here, the faster the stars rotate around the center, the greater the gravitational pull has to be. So from this idea, we can see that by measuring how quickly the galaxies are rotating, we can estimate how much gravitational pull is needed to hold them in place, and therefore how much stuff there is in the galaxy. So we can also do this another way, so by looking at the stars in our galaxy. So since we know how much stars weigh, simply by counting them and adding them all up, we can estimate how heavy the galaxy must be. So this is actually what astronomers did, and what they found was really surprising. So here I'm plotting the radius of the galaxy along the horizontal axis, which is so the distance from the center. And then on the y-axis or vertical axis, I'm plotting the amount of mass enclosed within that radius. So using the star counting method, as we move out towards the edge of the galaxy, the amount of mass that we can see in the form of stars increases a bit at first, as you can see by the steep line at the start, and then begins to flatten out and becomes constant. However, astronomer Vera Rubin, who is pictured here, she was the first person to measure what we call galaxy rotation curves in the mid-1970s. And what she found is that if we make the same estimate using the galaxy rotation, we find that the mass just keeps on increasing. So how can astronomers have found such a huge difference in our mass estimates? So what this means is that if there was only the stuff we can see in the galaxy, then the galaxy would break apart and the stars would go flying off. So we need some extra stuff to resolve this discrepancy that we can't see. And this is what we now refer to as dark matter. So when this initial discovery was made, there was a lot of skepticism, understandably. But as more and more data has been taken showing the same thing, it's become clear that this concept of some invisible matter needs to be taken seriously. And we now believe that all galaxies live inside a bubble or a halo of this mysterious dark matter, which extends well beyond where we can actually see the stars in the disk. So in truth, we don't actually know what dark matter is yet. But our best guess is that it's some particle that we haven't found that interacts through the force of gravity, but only very weakly with normal matter. So in fact, there are millions of dark matter particles streaming straight through your body every second without us even noticing, or without the dark matter even noticing us. So the reason we like this theory so much is because it also helps us to understand the structure of our universe. So when we look out into space, we don't see galaxies just distributed randomly across the sky. Instead, we see a web-like structure like shown here. So this is data from the Sloan Digital Sky Survey. And what this team did was to very accurately map out nearly 1 million galaxies in the nearby universe. So looking at this plot, every single dot here represents a single galaxy. So along this direction, so where the arrow is, we're looking further into the distance away from us. So the galaxies closest to the center of the circle are ones that are nearby, and the galaxies towards the edge of the circle are ones that are the furthest away. Now, the reason it's this triangle kind of shape is because as we look further away from us, more objects appear in our field of view. So what we're looking at here is essentially a galaxy map, with the red parts indicating where there's loads of galaxies, and the kind of darker black regions showing where there are very few galaxies. So we refer to this web-like structure as the cosmic web. So with these, and we call these long strands of galaxies, filaments, and where these filaments intersect, we refer to them as galaxy clusters. In between the filaments and the clusters, we have these vast expanses of space with very few galaxies in them, and we refer to these as voids. So this is what observers found. We saw this web structure, nothing uniform there. Now we can look at this another way and say, well, if I hypothesize that there's this type of dark matter which only interacts weakly and through the force of gravity, then what type of structures would it form? So this is what scientists who build big simulations of the universe did. And what they found was that the structure that we've been seeing in these galaxies is also seen in simulations of dark matter. So this is one of these dark matter simulations. And what I'm showing you here is a density map. Now, confusingly, the bright parts correspond to where there's loads of dark matter, and the darker parts are where there's no dark matter. So what this tells us is that the cosmic web of galaxies that we saw in the previous slide has a dark matter skeleton that we can't see. And this gave us the prediction that where we see more galaxies in the universe, we also expect to be able to find more dark matter. So far, our understanding is that this dark matter particle, elusive it may still be, pulls things together in the universe through the force of gravity. Even though particle physicists are yet to detect it, the astronomical community are in pretty good agreement that it exists. Dark energy, on the other hand, is less well known and therefore more hotly debated. So the first observation that led to dark energy being cemented into our standard theory of cosmology came in the 1990s, when two teams of astronomers used a new method to accurately measure distances to galaxies containing a certain type of supernova. So a supernova is what occurs at the end of a star's life when it explodes. And this image here is the remnant of a special type of supernova called a type 1a. So from our understanding of how stars work, we think that this type of stellar explosion occurs when the star reaches a specific mass. And because these explosions all occur at the same mass, we know that they must emit the same amount of light. So this type 1a supernova was identified as what we call a standard candle. And we can use these standard candles to measure distances. So this standard candle method works like this. So if we had all the supernova at the same distance away from us, they would all appear as bright as each other because they're emitting the same amount of light. And now, if we in fact move them, like some of them are further away, then even though they're emitting the same amount of light, they appear darker. So this is the same as if you stand under a street light when you're out at night. And then as you walk away from it, even though it's still shining as bright, it appears darker because the distance has increased between you and that light. So we can also measure the color that the light, that the supernovae emits. So the reason we want to do this is because when an object emitting light moves away from us, the light appears ever so slightly redder than when it was emitted. So this is a similar effect to when you hear a fire engine going past. So as it comes towards us, the sound of the siren is higher in pitch, and this corresponds to an increase in frequency. And then when it moves away from us, the sound becomes deeper, which corresponds to a lower frequency. So light actually does a similar thing. And when it is moving towards us, it appears ever so slightly bluer, which is an increase in frequency. And as it moves away from us, it appears a tiny bit redder, which is a decrease in frequency. So the reason we don't see this in our day-to-day lives is because the objects have to be moving really, really fast. And we need our telescopes to be able to detect slight shifts in the color to be able to measure this effect that we call redshift. So when we measure redshift of the galaxies that aren't close by, we find out that their light always appears a little bit redder. Now, this isn't because they're all moving away from us, but because the universe is actually expanding, and therefore the space between the galaxies and us, where we are on Earth, is increasing. So redshift is an indirect way of measuring the distance to an object, but this depends on the rate at which the universe is expanding. So going back to our supernova, if I measure the redshift of the supernova by measuring its color, which is what I'm showing here on the horizontal axis, and then measure the distance to the supernova and plot that on the vertical axis, the relationship between distance and redshift would look like this if the universe was expanding at a constant rate. So if the expansion of the universe is getting faster, then the relationship between these two quantities changes ever so slightly. And all the data points that we would collect from the supernova would lie above the yellow dashed line because it was accelerating. Now, if the universe's expansion was decelerating, the opposite thing would happen and the data points would lie below the yellow line. So therefore, by making these accurate measurements of supernova meant that scientists could figure out where the expansion of the universe was getting faster and faster or starting to slow down. So this is what two teams did, and they're led by these three scientists shown here back in the 1990s. And they found that the expansion of the universe was actually accelerating. So I'm not exaggerating when I say that it came as a surprise. The expectation was that the expansion of the universe was actually decelerating. And in the equations that they used to work this all out, they actually named one of the parameters the deceleration parameter, because we really didn't expect to find out that it was the expansion was accelerating. So, and this was such an important discovery that they were sent off to Stockholm and they won the Nobel Prize. So the idea of the universe was expanding more and more is most easily described by some sort of energy fueling that expansion. And so the term dark energy was coined. So from these two observations that I've described, brought about this idea of dark matter and dark energy, and have since been backed up by other methods that astronomers use to prove cosmology. And we have now cemented these ideas into our standard theory of cosmology. So this idea that dark matter pulls stuff together through the force of gravity whereas dark energy is acting against the dark matter by moving things further and further apart. But we still don't know what they are. Cosmologists are trying to test different models for what they could be to the absolute limit, and with many different tools and observations. And I would like to tell you now about my personal favorite, which is a technique called gravitational lensing. So the first research project I did during my undergraduate studies was based on gravitational lensing. And the way my supervisor sold it to me then was that to do gravitational lensing, all I have to believe is that Einstein was right. So I, at this point in my studies, had realized that Einstein was a pretty smart guy. So I thought that that wasn't a bad belief to have. And 8 years later, I still think the same thing. I'm still doing gravitational lensing, but now I realize it's also not quite that simple. So here is a photograph I took out of a very old window. Now, this might not seem like the most interesting scene, although the purple trees are quite nice. But if you look really closely, you can see that there's imperfections in the glass. And because the glass has different thicknesses at different points, it means that the buildings outside look ever so slightly distorted. So you can see this more closely. If I zoom in, you have these like wobbly windows. And this is because the path that light has been taken is actually being distorted by the glass in the window. And this is actually what we see when we look out into the universe, although it's not because the optics in our telescope are a bit dodgy. Instead, it comes back to this idea about that Einstein had about gravity. So within Einstein's theory of gravity, he showed that mass can bend space. So how I like to think about this is if you imagine a mattress or the cushions on your sofa, if that's where you're sitting now. And if you were to roll a marble across the surface of the mattress, it would travel in a straight line, which I've tried to illustrate with these arrows here. So if I was then to put a heavy bowling ball onto that mattress or some heavy weights, the surface of the mattress would be distorted and the marble would roll along a different path. So this is what happens at really large scales in the universe. But in this case, the mattress is space-time and the bowling ball is a clump of dark matter. So gravitational lensing is what we see when dark matter distorts the path that light travels on, in the same way that the bowling ball changed the path that the marble took on the mattress. So to demonstrate this more clearly, if we have light traveling from these distant galaxies that you can see at the top of the slide, if there was no dark matter in between those galaxies and our telescopes on Earth, we could see them exactly how they look at the top. So these kind of fairly circular on the sky and close together. But because the dark matter has changed the path that the light from the galaxies has taken, we actually see them in slightly different positions, how you can see in the bottom panel. And they're also, the shapes of the galaxies are slightly distorted and stretched around where the dark matter is. And it's this effect of the stretching of the galaxies and the displacement that we refer to as gravitational lensing. So we see this most clearly around galaxy clusters, as they contain loads of dark matter. So the galaxy cluster is roughly where this circle is. So you can see the kind of goldy coloured galaxies all clumped together. That's like the centre of our cluster. Now, if I then draw your attention to these giant arcs around the outside. So these are actually galaxies that are further away from the cluster, and the light has been distorted because of the presence of the cluster. So they wouldn't normally look like this. They'd normally just look like the spiral galaxies that I've shown you in previous slides, but they've actually been stretched. The images have been stretched because of the presence of this dark matter. So effectively, the galaxy cluster is acting like a huge cosmic lens, like a magnifying glass where the light refracted varies across the cluster. So this demonstrates a really important point. We can see this effect clearly around clusters because there's loads of dark matter there and the shapes change a lot, as we can see. Now, if I say this the other way around and say that the change in shape we see depends on how much dark matter is in that direction. So if we can measure this lensing effect, this stretching of these galaxies, then we can map out where dark matter is. And this is exactly what we try to do with this technique. So the team I'm a part of is called the Kilodegree Survey, or KIDS. And this uses the telescope shown here. So this is the Atacama Desert in northern Chile at the Paranal site. And on the top mountain is the BLT survey telescope, which I'm showing here. And on the bottom mountain is just down the road is the Vista telescope. And these two telescopes have been staring at the sky together over the past 5 or so years, and together have mapped out 5%, and this corresponds to about 31 million galaxies. So these galaxies are up to 10 billion light years away, which means that their light was emitted when our universe was less than half its present age. So there's some more kind of pretty images that we can make with kids. And so this is a galaxy cluster on the left-hand side. With the center of the image, you can see there's lots of galaxies all close together. In the top right corner is a field of galaxies. So this isn't a particularly dense region, and we wouldn't expect to find much dark matter there. And then at the bottom right is a nearby galaxy, which is not really much used to our cosmology studies. And we'd probably actually cut it out, but it's still very pretty, so we can still appreciate it. So I said with gravitational lensing, we wanted to find where all the dark matter is. So if you remember earlier in the talk, we also made this prediction that where you see lots of galaxies, you also expect to find lots of dark matter. So where better to look than a galaxy cluster, which is what I'm showing here. So when we use the lensing effect, we can reveal where the dark matter is on the sky. And we find that the dark matter, which I've kind of shown here in pink, is exactly where we expect it to be, which is right where the galaxy cluster is. So this has already tested that hypothesis we made at the start from looking at where the distribution of the galaxies and also from our simulations of dark matter, that this cosmic web really kind of matches up between the two. So we can actually make really large maps of dark matter that look like this. So again, confusingly, the bright parts are where there's lots of dark matter, and the bits that are darker are where there's much less dark matter. But we can see that this is very similar to those simulations of dark matter that we saw earlier on. And so we really are revealing this underlying skeleton of dark matter. So it's actually a really exciting time to be working on gravitational lensing, because there are currently 3 teams all working towards making the best maps of dark matter. When I did my first project, the biggest map was only 150 square degrees. And the kids team have just released this summer their latest one, which is 1,000 square degrees. So we've came a very long way in 8 years. Now, I've already told you there's lots of evidence that dark matter exists. So what more is this telling us? Well, from these maps, we can learn about how clumpy the dark matter is. And how clumpy the dark matter is can be predicted from different theories about what type of particle dark matter is. Now, gravitational lensing doesn't only tell us about dark matter. So as we look further away into the universe, we're actually looking further back in time. And so what we can do is we can map out the dark matter at different epochs and understand how it evolves. So by understanding how the skeleton of the cosmic web changes over time, we can investigate how dark energy impacts these structures and how they grow, and compare that again to our theoretical predictions of what we expect for different models of dark energy. So even within my short time studying gravitational lensing, we've seen huge advances in the amount of data which will help us solve this cosmic puzzle. And it's only going to get better. So we're currently starting to all get excited about several new telescopes that are being built exactly for this purpose, one of which I'm showing here. So this is the Vera Rubin telescope, also in northern Chile, but on a different site. And it looks like a construction site because it's still being built. So this new telescope will observe more than half of the sky, which is huge in comparison to the dark matter map that I just showed you that only covers 5% of the sky, which was done with a kids survey. So with this telescope, we'll also be able to look even further back in time by looking even further away. So we're going to see a huge increase in the kind of sophistication of our data in both size and quality. So I've just left a few key points here which sort of summarize where we're at in cosmology right now, and specifically with gravitational lensing. Hopefully I've convinced you this evening that although we don't know what 95% of the universe is, we think we're well on our way to finding out. And in doing so, there's going to be some incredible new findings which will impact our fundamental understanding of the universe. Okay, thank you for listening.
Cool. Thank you very much, Naomi. You will have to imagine the round of applause, which is no doubt happening among people that's watching. It's the one downside of these remote talks. You don't get the immediate kind of thing. Had some good questions coming in through YouTube. A slightly technical question from Aprojit, if you don't mind. So he noticed in that the galaxy rotation curve that you showed, which is kind of the mass within radius graph, the rotation curve kind of matches up with what you would expect from the stars initially, then only diverges as you go to larger radii. So he's wondering if that means you only have regular matter in the center and dark matter in the outside, or what's going on there.
So I don't think we're exactly sure, but I think yeah, you have more regular matter towards the center, and then we think they live inside this kind of bubble of dark matter on the outside instead, is the best description of it. Yeah.
Great. And we had a question from a user called Outer Space, who's asking about rotation in the universe. They're asking why things in the universe rotate.
So the galaxies that I was describing, they rotate under galaxies. So it's this balancing of the kind of what we call the centripetal force and gravity. And that's our main reason. But yeah, so I think that kind of explains why all things do. In our own solar system, we rotate around the sun as well. And then we have rotation in our galaxy, and then galaxies tend to kind of move around in clusters a bit as well. But yeah, it's generally governed on these large scales by gravity primarily. But there's different things at work.
Great. And user Outer Space is saying his actual name is Tushar Dubey. So yes, thank you very much, Tushar. Yes, thank you very much, Naomi. That was a fascinating talk. I always feel like it's a very exciting time to be an astronomer or a cosmologist, kind of facing this new century where we have like 95% of the universe waiting for us to discover. It's a very
it's so much left to discover and so much data coming in as well. It's like prime peak cosmology time.
I cannot wait to find the answers. So thank you very much to our headline speaker. I'm going to hand over now to the Cambridge Astronomical Association, who unfortunately, as I said at the start, it's a little bit cloudy, so we don't have we don't have some stargazing for you, but I think we have a fun second talk all about the nearest very big black hole. So yes, over to you guys, the Cambridge Astronomical Association.
Thank you, Matt. Yes, indeed. Looking at the all-sky camera at the moment, and it's solid cloud here above the observatory, so we won't be able to bring you any live stargazing, I'm afraid. But as a consolation prize, we've got a little talk for you about the black hole in the center of our galaxy, our black hole. And this is one that we have presented before for our Cambridge Young Astronomers program. So if there are any young astronomers out there, do join us. And tonight, the second talk is going to be given by Brian Lister, who is our Vice Chairman of the Cambridge Astronomical Association and also coordinates that Cambridge Young Astronomers program. And I can see that Brian is getting ready and has prepared his screen. So without further ado, I'll hand over to Brian.
Okay, thanks very much, Paul. Right, our black hole. Well, we start with the galaxies. In about the 1920s, there was a big argument as to whether galaxies were part of the Milky Way. But Edwin Hubble in 1923 soon proved that galaxies were indeed separate from the Milky Way. And 20 years later, Carl Seyferts noted that some group of galaxies had very bright centres, and these were named Seyfert galaxies. 16 years later, quasars came along. These have very bright nucleus. And a little while after that, with an even more energetic nuclei were Blazars. So what are these three objects? Well, since I'm talking about black holes, it sort of gives the game away. Here's an artist's impression of a supermassive black hole seen edge on with the accretion disk swirling round it. Now, if you were to plonk this into a galaxy and look obliquely at the galaxy, you'd see the galaxy had a bright center, and this would be a Seyfert galaxy. But if you look down at it, you'd see it had a very energetic center, and that would make a quasar. But if you look straight down at it, down the relativistic jets that squirt out, like looking down the barrel of a gun, you'd see a blazar. So these three objects are one and the same thing. And it was way back in 1971 that Donald Lyndon Bell and Martin Rees, who work at the Institute of Astronomy in Cambridge, proposed that at the centre of the Milky Way, there would be a supermassive black hole. They didn't have long to wait. 3 years later, radio astronomers in America detected the supermassive black hole. And in this radio image, a later radio image, you can see the supermassive black hole as the red splodge. It was subsequently called Sagittarius A star. But the trouble with a spiral galaxy like we live in, as you can see from the main picture, is that there's a lot of gas and dust in them, which obscures our view of the center. If you see from street lights, you can see that the mist acts like dust and it gradually extinguishes the light quite quickly. And in the bottom picture, we can see looking towards Sagittarius, where our supermassive black hole is. But against the background of stars, you see silhouetted the gas and dust that stops us seeing right into the center of the galaxy. But astronomers always have tricks up their sleeves, and by using giant telescopes like the Keck telescopes here and infrared, we can get round. On the top picture on the left, it shows part of the Eagle Nebula in visible light and the same area in infrared light. And here you can see you're seeing through the gas and dust to hundreds and hundreds of stars beyond them. So this is a good way round it. And here is the area around our supermassive black hole. And you can see stars orbiting around something. Obviously, you can't see Sagittarius A star, but you can see where the stars are going round. This is an animation made over several years of observation. Now, if we just look at the center portion, we can see that stars start to orbit round Sagittarius A star, that little white star. And you can see one yellow orbit is nearly complete, and now a pink orbit beneath it is also complete. And these two orbits are shown in the diagram on the right. And to scale, I've added a orange ring, which is the size of Neptune's orbit, and that's superimposed where our black hole is. And as you can see, the star on the yellow orbit, S2, the S stars are ones that orbit Sagittarius A star. You can see that got very close in 2018 to within 4 times the Neptune Sun distance, by which time the gravity had accelerated this star to well over 2.5% the speed of light. So that made that the fastest moving star. And they worked out from the orbits of these S stars that the supermassive black hole at the centre of our galaxy was over 4 million solar masses. But since a black hole is no size at all, but the event horizon is shown on this diagram. That's the boundary at which light cannot escape the immense gravitational pull of the supermassive black hole. And you can see it's on the scale of the solar system, you can see it's about 17 times the size of the sun, or about 1/3 of the way to Mercury. So on a planetary scale, the event horizon of our supermassive black hole, it's actually very, very small indeed. Was the Milky Way ever a quasar? Well, yes, once the supermassive black hole had formed, it started feeding on material and the quasar was formed. And while material keeps falling into the black hole, it will carry on being a quasar. But one thing we can't know is how long it was a quasar for when our galaxy was young. Because quasars can last just a few million years, or they can go on for hundreds or even thousands of millions of years. Will we become a quasar again? Simple answer is yes. In about 4 billion years time, the Andromeda galaxy will come close to us. It's approaching us, and these four photographs or images show how it will appear. And when the galaxy gets close enough, it will start to disrupt the center of our Milky Way. And once again, material will start to fall into the black hole, and we will be a quasar again. And since the Triangulum galaxy is gravitationally bound to the Andromeda galaxy, that may well join the train wreck as well. Has our supermassive black hole had a meal recently? Well, from the Fermi Gamma Ray Space Telescope launched in 2008, it made a map of the sky. And here we can see top left, the entire sky, and the red and yellow is the Milky Way running across the sky. But after the images were processed and enhanced, you can see on that map now 2 orange blobs, one above the plane of the galaxy and one below. And in the diagram on the right, it shows that these Fermi bubbles, as they were known, are the fossil record of when we were a quasar. And these bubbles stretch 25,000 light years above and below. And it happened about over 5 million years ago when the Sagittarius A star consumed up to 100 solar masses of material over a period of 1 million years. And during that time, we would have been a quasar. How about much more recently? Well, from the Chandra X-ray Observatory, it caught a flare in September 2013. And in the animation on the right, you can see there's a steady wobbly blue image, and that's just a magnetar, which is a neutron star with strong magnetic field, just in the line of sight and nothing to do with our supermassive black hole. But repeated is the flare that Chandra saw. What was happening here? Well, astronomers think that it was probably something quite small, such as an asteroid that got eaten. And just over a year later, there was a smaller flare. So maybe another asteroid or a fragment of the original asteroid that fell in earlier. So that was in 2013. In 2012, a gas cloud was discovered heading towards Sagittarius A star. And computer animations showed that as it swept past, material would be stripped off it and fall down into the black hole. And this would happen in 2014, a couple of years after the discovery. So astronomers prepared diagrams for the media. They drew up their chairs, sat down and waited to watch the fireworks. 2014 came and went. Nothing happened. The gas cloud G2 just swept by and nothing went into the black hole. But why? They guessed that probably their calculations were wrong and that the gas cloud G2 was much more massive than they first thought, and so it was able to sweep by. Then, just last year, in May, there was another event, another brightening of Sagittarius A star, caught by one of the Keck telescopes in infrared. Again, you can see it here repeated. So what were the possibilities? Another asteroid being eaten? Or maybe the S2 star, the one that was accelerated up to that enormous speed. You can see it on the diagram there, that passed 2 years ago. And maybe some material did get stripped off it and ended up in the black hole. The third option was the G2 gas cloud that went by in 2014. Again, maybe material got stripped off it and ended up going into the black hole. Well, astronomers mulled over it and they eventually came to the conclusion that it was option number 3. So what are these G objects? They're gas clouds, but it appears that they were binary stars that have merged due to their close proximity to the supermassive black hole. And so then they are surrounded by a cocoon of gas, so we can't see these stars. So that's why these gas clouds are much more massive than we first thought. So they look like a gas cloud, but behave like a star. And as you can see, in the last couple of years, 4 new ones have been discovered. And there'll be some close encounters coming up in future years. And then 3 months later, they found another S star, S62. And again, I've popped it on the same diagram as earlier. And this time you can see it came actually within the orbit of Neptune's orbit. It would have come with, it will come within the orbit of the Uranus Sun distance in a couple of years' time. And by then it will be accelerated up to 7% the speed of light. But of course, all these orbits of these S stars mean that we've now got a good handle on the mass of Sagittarius A, our supermassive black hole. And it's 4.31 million solar masses. There's a number to bore your friends with. And then just before Christmas, it was proposed that Sagittarius A star might consist of 2 black holes. But since the star S2, the yellow orbit, doesn't seem to be affected means that the second black hole can't be a supermassive one. It's probably less than 100,000 solar masses, which makes it a rare and an unusual intermediate black hole. So astronomers are keen to see if they can find that one. And then finally, just a couple of months ago, the Very Large Telescope in Chile, which is actually 4 large telescopes, found 5 new S-stars, S4711 up to S4715. And 2 of them are going to get very close to Sagittarius A star. I've put them on the diagram, and you can see that S4714 is going to get the closest. And these 2 probably will be Squeezars. So let's look at these Squeezars. Squeezars were first proposed in 2003. And what they are is, as a star approaches the supermassive black hole, it's squeezed out of shape and heats up. Then as it goes round the black hole, it will then reform it back in its original shape and cool down. But because the physics of Albert Einstein take over from Newtonian physics, the orbit is altered. And the next time the star comes round, it will come round closer to the black hole. So each orbit, it will get closer and closer to the black hole. Now, these 2 Squeezar candidates, you can see that S4714, the one that is got very close, is going to get to within the Sun-Saturn distance of Sagittarius A star, by which time it will be even faster than S62. It will be up to about 8% the speed of light. And the other Squeezar candidate doesn't get as close, but it's got the shortest orbit of all of the 40-odd S-stars of 7.6 years. So each 7.6 years, it will get closer to the black hole. And that's where I'll stop. There's a lot going on in our black hole. Lots of data has got to be confirmed, but keep an eye on it and we'll find out if these really are Squeezars. Thank you very much.
And thank you very much, Brian. The black hole at the center of our galaxy has been in the news recently as well, obviously, with the Nobel Prize going to Andrea Ghez and Reinhard Genzel for kind of a confirmation that these things are going on. So yes, black holes are very interesting.
Good fun.
As always, exactly. Yes, cheers, guys, and thank you to everyone at home. Thank you who has been contributing in the comments and just watching. We will see you next week, and fingers crossed for clear skies.
Thank you.
See you.
Bye.
Bye.
Wonderful.